Okay, maybe we should get going. So, yeah, lecture 4 in this course in Amplitudes of Classical Gravity. So the topic of today is going to be the waveform. How we can understand the waveform from the perspective of quantum field theory, how we can compute it using scattering amplitudes. Well, firstly, we have some classical sense of what we mean by the waveform. Well, classically, the waveform is some measurement of the local metric, or the deviation from the local metric from the Minkowski, the flat space metric. The metric deviation, h mu nu. So it's basically the difference of the full space-time metric from the flat space metric at your detector. Obviously, it's projected really onto the arms of the detector to get a scalar, to get a number out of this on a, a tensor. But from, I mean, this is going to be good enough for us. Now, in quantum field theory, we don't make direct measurements. We have to have, talk about expectation values. So you have in mind some experiments that's repeated many times. On quantum field theory, we have to consider expectations. So the obvious thing to start thinking about is the expectation value of the actual graviton, the field of the graviton themselves. So we consider the basic plan is going to be to consider some expectation value of h mu. Okay, now, there's a saying in quantum field theory, which goes back, is my understanding, to Bryce DeWitt, the early people who studied gravity as a quantum field theory. And the slogan is, I'm probably grossly abbreviating it here, but the slogan of DeWitt is that the only observable and let's say just in gravity, is the S matrix. This was a slogan I heard when I started doing my PhD, and I found it very confusing because I knew people were, measuring, people were talking about gravitational waves, and gravitational waves, not sort of mysterious slogan. But in a sense, what I'm going to do today is explain how the slogan really does apply to gravitational waves. So we see that the gravitational waves can be expressed in terms of amplitudes, which are the S matrix elements. Okay, now, yeah. So just some comments on literature. So the lecture today will be based on a paper, this one here. It's reviewed in this review I mentioned a few days ago, lecture 2, I think, 13025. This is the review. But I'll come back to, so there's one point in this paper where I'll come back to it a little later. Now I'm still going to restrict to scattering. So, we're going to have in mind that we're scattering black holes. We shoot them at one another. There's some scattering event, they come out, and there's gravitational waves. Okay, of course, as I said the last time, the idea is that once you've done this computation, you take the information and put it into some sort of machine, like some EOB machine, and then you can use the information in band states. Now, the idea from last time was, to start from scattering amplitudes and obtain results for observables was as follows. Good idea. From the last lecture from yesterday. So there's sort of recipe here. There's a three-step recipe. You start by picking an observable. Which makes sense in both the quantum theories and classical theories, classically and the second thing to do is to pick a state which happens to be in the domain of validity of the classical approximation. So we call the state psi. Classical approximation. So, well, again, I should maybe say an initial state. So then the final state is obtained by acting on the initial state with the S matrix. So that means that we can compute the change in our observable, an observable O. Can compute the change in the observable in terms of amplitude. So yesterday I applied this algorithm in the case where O was the momentum. We picked one particle and we looked at the change in the momentum of that particle during a scattering event. Today, today I'm just going to pick so we just apply exactly the same algorithm to a different observable, to H mu. Okay. All right, so let's just go through this step by step. I suppose step one. Well, we've already said that that our observable is going to be H mu. So the expression we had for H mu at some position x is a sum on velocities of gravitons, integral over the momentum of the gravitons. Annihilation operator, e to the minus I k dot x. And there's another term here, epsilon star, creation operator, and e to the plus I k dot x. Let me just write that as plus Hermitian conjugate, plus HC. So you just have to take the Hermitian conjugate of everything you see here and add it on again so that the whole thing's real, right? Yeah, it's just abbreviate the writing a small bit. Okay. Very good. So this is the observable. Now, a couple of remarks. Now, our observable yesterday was the momentum. H mu nu is different from the momentum in as much as H mu nu has a gauge dependence. It's visible here, for example, in the gauge dependence of the polarization vector. So this is really a gauge dependent quantity. And in that respect, calling it an observable is, well, you might not think it's directly observable. It's only observable up to some gauge choices, right? So like the momentum p. we could try to compute something that is more gauge invariant. For example, in linearized theory, the Riemann tensor, the linearized Riemann tensor, is invariant under linearized diffeomorphisms. So we could instead compute so this would be the linearized Riemann tensor, which I just obtained by acting on this expression for h mu nu with appropriate derivatives. So that's a sensible thing to do. We could extract out of that, for example, then psi4, the Newman-Penrose psi4. And that's actually the attitude that's adopted, I think, in these papers in this review. We computed the Riemann tensor because, well, look, this gauge dependence isn't really great, and we wanted something that was very solid and makes sense. But in the next lecture, I want to come back to this issue of the gauge dependence. So I'm just going to work with h mu nu. In fact, it's in the manipulations that I'm going to go through in this lecture. It wouldn't really be much difference. The only thing is, because Riemann tensor has various derivatives, I'd have various momentum running around in these expressions. It doesn't make it, actually makes the calculation a little bit shorter to not put in those derivatives, and I'll address the gauge issues tomorrow. So maybe for now, I'm just going to say it's an observable in quotes. Because of this gauge dependence issue. Okay, so that's step one. Well, step two, we have to pick a state. Now I'm going to use exactly the same state as last time. Exactly the same state as yesterday, namely psi will be an integral d phi of P1 and P2 for the two particles that I'm scattering. I'll put them in wave packets. Phi P1, P2. I will translate one of the particles with respect to the other. So the wave packet will, or the state will take that form. Now, it's exactly the same state as yesterday, but I'm now taking h bar equals 1. I'll take the units where h bar equals 1. The issues of what happens with the h bar are exactly the same in this context as they were yesterday in the momentum. There's no real need to go through it again. At tree level, everything is very nice. When you start going to higher orders, loop calculations, there are certain cancellations that you need to be careful about. So exactly the same issues. And I'm also, in order to extract a classical observable, I would need exactly the same inequalities as before. Those inequalities were about the state. Right? We had to pick a state within the domain of validity of the classical approximation. What observable you measure in the future, that's up to you. So you've got a classical state, and under that assumption that the dynamics preserves the classicality. So you don't evolve from a classical situation to a quantum situation. Okay, very good. So the third step then basically is say, well, look, my final state is SI, so I can compute the change in my observable. Well, so it's psi S dagger h mu nu of x S psi minus psi h mu nu of x All right, now here there's actually something that's a little bit different to yesterday. So the difference is in the case of the impulse, we cared about both terms, but in the case of the waveform, the second term here is just zero, this particular. Okay, so to see why this is, well, we can just go ahead and compute what this thing looks like. Yeah. So, well, I'll just insert the expression for h mu nu here to this expectation value. So the result will be sum on felicities, integral T5K. Our polarization vectors. And the expectation value of the annihilation operator of the gravitons on the state psi, e to the minus I k dot x, plus complex conjugate. I'm writing plus complex conjugate here instead of plus Hermitian conjugate because that's just a pure, that's a number, it's not an operator. I'll use these abbreviations more and more today and tomorrow. Okay, now, but this expectation value here of the annihilation operator is zero, and it is zero just because the annihilation operator of the gravitons acting on the state psi is, well, writing out what our state psi is. P1. There is an annihilation operator acting on this ket here. Now the ket has particles in it, has two particles in it. But those particles are, the black holes, the H particles, the scalar particles. So those are created by creation operators of the scalar particles, which have nothing to do with the annihilation operator of the graviton. So the annihilation of the operators of the gravitons passes straight through those creation operators for the two scalar particles, and then it hits the vacuum. But the annihilation operator of the graviton annihilates the vacuum. So this whole thing is zero. To put it in words, the annihilation operator of the graviton annihilates the state because the state has no gravitons in it. So it just hits the vacuum again. Okay, so this term here is just zero.
You could start with, if you had started with another state where there was graviton already, then this would not happen.
That's absolutely right. Yes. I mean, at this stage, there's no particular reason for me to do that. I mean, I want to scatter a bunch of particles. I don't want to scatter particles of gravitational waves. Having said that, I'll discuss this in more detail tomorrow, and I'll start doing exactly what you're talking about. But for now, the picture you have in mind is a pretty straightforward picture, a simple-minded picture. It's a naive picture. I've got two particles. I'm scattering them at one another. I didn't need to put in any gravitational waves. Why would I do that? So then you'll find that this happens here. But yes, it's an interesting point. Psi h mu nu x psi equals 0. In other words, the expectation value of the initial metric deviation is 0. So I think this is an interesting point, and I'll come back to it tomorrow, but it's that for now, it's not really going to bother us. I mean, if you're sort of thinking it's a little bit funny, well then, all the more reason for the lecture I'm going to give. Okay, so anyway, so coming back here, this is our change in observable. Now we've seen that this term here is 0. So the whole observable is just this combination. The observable is then just the future expectation of h mu nu. So I'll define it just to be a non-blackboard bold h mu nu, so just a normal h mu nu. So this will be psi s dagger operator h mu nu. And that is expanding the h mu nu again as here. There will be sum and helicity integral over the graviton momenta, graviton phase space, polarization vectors. So, and then the expectation value now of this annihilation operator, but sandwiched with S matrices. So it doesn't get to act on psi and make it vanish as it did for this term. Plus complex conjugate. Okay, so this is the quantity I want to compute, discuss in more detail today. For now, I'm just going to introduce a little bit of notation to organize this object a little bit more. So I'll call it an integral of j mu nu of k e to the minus I k dot x plus complex conjugate, where the j mu nu is, well, everything else that's here. So the sums on helicity, polarization vector, this overlap of states and operators. Okay. Now I want to do some of the integrals to simplify this thing. Now, we know that what we're trying to compute is something related to the classical gravitational field. It's in particular, the classical field that we get by scattering a bunch of particles and measuring the outgoing gravitational waves at infinity. So you would think then that this h mu nu should fall off like 1 over distance, right? Because if I integrate it over a big sphere, there should be some finite amount of energy that's being transported in the gravitational waves. The area of the sphere goes like r squared. You've got to square this thing to get the energy. So, so you'd expect this h to fall off like 1 over r. And what I want to do now is show you how that follows in this setup here. And it follows by performing this integral over the graviton momenta. I'm going to use a stationary phase argument to do this integral. Okay, so it's nice to get rid of integrals that you don't need to do. Integrals are hard. Okay. Yes. So in order to do this integral, I'm going to slightly change my notation. So far, I put my observer at a position x, which is maybe not an unreasonable thing to do. But for the purposes of this little calculation here, I'm going to just switch the notation so that my observer is at a position z. And you'll see why I want to do that in a moment. So I'll place observer at coordinate observer. Position Z mu. Okay, so now then you make a definition of the actual integral I want to do. I'm going to let my integral be I mu nu. I mu nu of Z, so that's where our observer is. This integral d5 of k, j mu nu of k, e to the minus I k dot x. So I'm not writing plus cc because, you know, it just goes along the same way. So I'll just talk about this particular part. And then when I want to write an expression for the h mu nu, I'll just start adding the cc back on again. So just breaking it up for convenience for now. Thank you. Yeah, muscle memory. It's tough to. You will see why I want Z. I'm not doing this just to confuse myself. Okay, so let's write out a little bit more detail here about this integral is. So this integral d5k is an integral, well, d4k. There is a theta function setting the momentum of the gravitons positive, a delta function setting the graviton momentum on shell, the j mu nu, e to the minus I k dot. Okay, so I'm going to break this integral up into an integral over frequency and the three-dimensional components of the graviton momentum. Now I'm going to keep the frequency integral along for the ride. So we're not going to do that integral, and I'll end up with an expression for the h mu nu in frequency space. So there'll be an integral then d omega, that's the zero component of the momentum, the frequency. Well, up to h bar the frequency, but h bar is 1. Okay, integral then d3k. The theta function is now just a frequency space theta function. This delta hat here is a delta hat setting the norm of k squared, so vector k, three-dimensional parts of k equal to omega squared. We'll have j mu nu now as a function of omega and k vector. So that was k mu, the four components of k. Here I'm breaking that up. E to the minus I k t, e to the plus I k dot z. So the vector components. Very good. So now I'm going to do the integral over the magnitude of k with this delta function. So the delta function here is a delta hat of omega minus k vector times a factor 1 over 2 omega. And so it's a so I'm using here the relation between delta of a function of a variable and then the delta of the variable evaluated at 0 divided by the Jacobian f prime, the first derivative of the function. So the first derivative is 2 omega. If this looks a little bit unfamiliar to you, another way of thinking about it is I've just changed variable here from d omega to d omega squared. Doing that, I'll pick up a 1 over 2 omega. And then I'll do the integral d omega squared with this delta function. Since there's a theta function here making the omega positive, I don't have to worry about the solution where omega is minus norm of k vector. Right? So, very good. I'll still have the integral from over omega. I'll write it as integral d hat omega from 0 to infinity because of the theta function. Now I've done the magnitude integral of k using this delta function. Well, there will be an integral over the direction of k. So the the angles of k vector. I'll write it as d omega. So those are the angles of k. Maybe I'll write it as d omega k. Now this integral d3k involves dk, d magnitude of k squared, right? Magnitude of k squared was omega squared, but I've got a 1 over omega here. So I have a net 1 power of omega upstairs. And now I have to start worrying about 2 pi's, which I've hidden away for most of these lectures. There was a 1 over 2 pi cubed here, but a 2 pi there. So I'm left with a 1 over 2 pi squared and a 2. So that's a total 1 over 8 pi squared. Thank you. It's an omega t. Thank you. Good. Yes. So there's the j mu nu here. Now it is j mu nu of omega k hat. So k vector has magnitude omega, and there's still the direction k hat, which I'm integrating over. And then these terms here are e to the minus I omega t. And this term is going to be an e to the I omega k vector hat. Let me pull out the magnitude of the position of the observer. So the observer is at a position z, but the distance is r. So the magnitude of z, we'll say, is r. And then there's just these dot products of k dot z hat. Where okay. Very good. So now the integral I want to do, the remaining integral I want to do is this integral over the angles in k vector. So this integral over the sphere here. Now the distance r here, by assumption, is very, very big, right? I mean, you have in mind some situation like a LIGO situation where we've got some gravitational wave event very, very, very far away. So this r is astronomically big, and the phase here is oscillating very, very rapidly. So I'll do this integral by stationary phase since r is big. Okay, now it's convenient to line up the direction of the north pole of the k integral. So I'm doing an integral over sphere. So I line up the polar axis of the k integral with the direction that my observer is in, right, which is the z direction. Right? So in short, I'm going to choose the z direction of k to be the z direction of my observer. This is why I wanted an observer at position z. So I really didn't want the z direction of k to be in the x direction of the observer. I did try to do that, and it caused me a lot of headaches. So they would choose the polar axis. Direction z hat of the observer. Okay, so here's z hat. Here's the k's that I'm integrating over, the unit vectors, these unit k's. obviously there's an angle theta between these two vectors. And the phase then that I'm interested in, the phase of this exponential here, of this oscillating factor. So the phase is I omega r cos theta. Okay, now theta is one of the variables I'm integrating over. So the stationary phase condition is the thing that you get by differentiating this phase. So the phase will be stationary when the derivative of cos theta is 0. And so that is when sine theta, derivative of cos theta is 0. So, so there will be 2 stationary points. So I want to draw pictures of these. So the first will be at theta equals 0. So now, at theta equals 0, we have a situation where k vector is in the direction of the observer. So if we have some source here and some observers over here, at theta equals 0, the waves with the wave vector k vector are pointing from the source to the observer. The second stationary point is theta equals pi. It's the other way I can get sine theta equal to 0. So then, if we have we have some system and some observer, well, now the waves are going from the observer to the system. And they're going in the opposite direction. And this corresponds to a choice of boundary conditions. Retarded boundary conditions or advanced boundary conditions. Retarded boundary conditions correspond to waves coming from sources to observers. Advanced boundary conditions, essentially the observer shooting waves up the source. Right? So here's where you get to feed in our boundary conditions. And of course, the boundary conditions that are relevant to us are the retarded boundary conditions. These two. This phase space integral that I'm doing here is just a completely general phase space integral. So it would apply just as well in the situation that you're shooting waves up the system, waves coming out. But the actual physical application is to the situation where waves are being generated by a source and coming out. So I'm going to forget about the theta equals pi stationary point and just work with the theta equals 0. This is the one that's that corresponds to retarded boundary conditions. Use retarded boundary conditions. So I'll work only with the stationary point. Very good. Okay, so now So at this stationary point, we can write points on the sphere. So you know, this phase is stationary now when theta equals 0. So for points near theta equals 0, I'm going to write an expansion for what they look like, and then integrate over all points in that neighborhood. So we'll use a little bit of notation. So notice near theta equals 0, near the North Pole. So the points on the sphere have the form, so these will be the vectors k. So allowed vectors k near theta equals 0. So they can be given in terms of two coordinates, which I'll just call A and B. So I have in mind here that our sphere, let's say this is the North Pole, there's some essentially some tangent plane to the North Pole here, which is a two-dimensional plane. And I'm going to have some axes on these planes with coordinates A and B. So there will be an A in the x direction, B, sorry, mixed notation here. A in the x direction, B in the y direction. And then the z direction, well, it has to be a unit vector on the sphere. So there's a 1 minus a squared minus b squared, a z hat here. The dot product that we're interested in this integral has k dot z. I mean, it's also multiplied by this omega r factor. But I care about k dot z hat. So that's just picking out the square root term. Now, you know, I'm just interested in points near my stationary point. So the a's and b's are small, and I'll expand in terms of them and just keep the leading term. So there's going to be a 1, well, leading non-trivial term, minus a half a squared plus b squared. Okay, so our integral then so this I mu nu back here in your board, I mu nu c going to be the integral from 0 to infinity d hat omega. Let me try and pull apart the terms that I don't care about. So the I'm interested in this omega k integral. The omega over 8 pi squared will come out of it. So will that e to the I omega t. This integral over omega now, I'm going to do it by stationary phase. So what that means is that I'm just going to integrate over a and b. Now I know that since the phase is oscillating very rapidly, the only points that are going to contribute are those points with small a and b. But then I can extend the integral, and this is the trick of the stationary phase integral, I can extend the integral over a and b to integrals from, you know, over all a and b, from minus infinity to infinity, right? Since the phase is oscillating very rapidly, a's and b's, which are large, will just give 0 to the integral. So I don't have to worry about them. So the integral will localize itself into small a and b, which is the part where there's actually a sphere. So I get to rewrite this as just an integral dA dB. The j mu nu there is going to become j mu nu. Now it's really j mu nu of omega and omega k vector, but on the stationary point, k vector is equal to z vector, z hat. This is, so I can in fact take it out of this a and b integral. And what remains is this term here, e to the I omega r k dot z hat. So I can simplify it with this expression here, e to the I omega r. 1 minus a half a squared plus b squared. Good. Now, so let me simplify this a little bit more. omega over 8 pi squared, e to the minus I omega. Now this omega minus I omega t combines with this e to the I omega r to give an e to the minus I omega t minus r. I'll pull out the j mu nu. And then I have a Gaussian integral over my a's and b's times I omega r. Okay, now this is a nice well, a standard Gaussian integral. There's a factor of 2 pi from the Gaussian integral, and then just a factor. Well, Gaussian integrals give you square roots of the object multiplying the Gaussian, but I've got 2 of them, so we'll just get 1 over I omega r. Okay, and that's the 1 over r that I actually really cared about, right? So I wanted to see that this h mu u was going to fall off like 1 over distance. I mean, physically it has to, otherwise you'd be doing something wrong. And in this way, you see that indeed it does fall off like 1 over distance. Putting together the factors, there's a minus I from that 1 over I downstairs. The 8 pi's cancel against that 4 pi, 2 pi to give a familiar kind of 1 over 4 pi r fall off. And what remains is a frequency integral of the j mu nu. Okay, so that's the stationary phase integral. Okay, I wanted to make a couple of comments at this point. In notational terms, I'll switch back to putting my observer at x, where the observer used to be. So the reason I didn't like having a z in this calculation was that it confused me between the x's and the y's, z's here. So then we'll have I mu nu of x is minus I over 4 pi r. Yeah. So I'm going to define t minus r to be u. X hat. So u is defined to be t minus r is the retarded time. Yeah, so it's also satisfying to see the retarded time coming out of this calculation. You'd expect that, because of the time of flight, the observer would see the source at a much earlier time. If you look at the advanced, the theta equals pi stationary point, you'll get the advanced time, the t plus r. It's another way of seeing that this is associated with the retarded versus advanced boundary conditions. Now, another physically satisfying aspect of this calculation, the stationary phase calculation, after the stationary phase, the graviton momenta So the graviton momenta are k mu. So the k mu is this thing that was the argument of j mu nu. The j mu nu from here involved the momentum of the gravitons. Here we see that the momentum of the graviton is omega x hat. So it's a frequency times 1 comma x hat. I'm going to write this as omega n mu. So n so this is a null vector, and one way to think about this is that it's the null vector directed from the source to the observer. So this n mu will be it's sort of the basic 4-vector we have left in the problem at this stage, so it's a kind of an important object. Feature a lot tomorrow. But one thing to note, right, is that after the stationary phase, the graviton momentum are directed from the source to the observer. I mean, it's this picture here. And that's a good thing because, you know, I mean, when you think about the gravitons are supposed to be the particles that are shooting from the source to the observer, so it is good that the gun is aimed in the right direction, if you want. Okay, so I've already emphasized that h goes like 1 over r. Ah, that's right. So, and finally, do I want to rub that out? Let me just go back over here. So, and as a last comment about this, number 3. So you can see this paper I mentioned, 2101 point something, for an alternative derivation of exactly the same point. It's a little bit more, well, this is sort of a, here I use the stationary phase in it's sort of a, well, quickest form, let's put it that way. Because I wanted to fit the discussion into the lecture, but in the paper we went through a longer version of the same calculation, where you really see the advanced and retarded boundary condition. You see that the Green's functions, the retarded and the advanced Green's functions, come out of the calculation, and you can understand in a more direct way how these two stationary points relate to retarded and advanced. If you didn't find this completely convincing, well, then you can go back to this paper. Okay, and this derivation has the great advantage that it's more obvious where the factors of 2 pi, etc. come. Okay, very good. So after this calculation, we can come back to I kind of did rub it. The h mu nu. We've now reduced the observable to the observable in the form. So our h mu nu of x is, well, there's this minus I over 4 pi r. Now filling in what the j mu nu was. The j mu nu had at the sum on helicities. We still have a frequency integral to do. There's polarization vectors. space. So there's the expectation value of quantum field operators. And then e to the minus ik dot x plus complex conjugate. Yeah, so maybe a good way of saying this is, yeah. So we evaluate k as omega n. Sorry, it's not e to the minus I omega k dot x anymore. We just have e to the minus I omega u. With k evaluated as omega n. So hopefully that's it in there. Yeah. Okay. Yeah. Very good. So we've got it down to these forms here. So you can view this as an expression for the waveform in frequency space, right? So obviously it involves this object here, and this object here is what I want to start talking about next. One comment, let me put the CC over here. So it gets back to this business of k and omega n. Now the polarization vectors, they don't care, polarization vectors care about the direction of your momentum. They don't care about the frequency. So we choose polarization vectors just depending on the direction. In other words, the polarization vectors, I mean, I talked about how we pick a basis of polarization vectors. You choose some gauge zeta, so that zeta dot epsilon equals 0. The epsilon satisfied k dot epsilon equals 0, right? So this way you reduce a 4-dimensional set of possible vectors to a 2-dimensional choice of the two physically relevant polarization vectors. But you see, the only way k entered there was in k dot epsilon equals 0. And since k here is evaluated at omega n, the omega is just going to cancel out. So the polarization vectors just depend on the choice of n. So you can just regard these polarization vectors here after the stationary phase computation as polarization vectors just depending on n mu, not on k mu anymore. So I could pull them out of that integral. So not a big deal. And this will be maybe it'll be a little bit more relevant for us tomorrow. I'm going to talk about polarization vectors as a function of n tomorrow. For us today, it's just a remark. Let's say epsilon h mu of k is the same thing as epsilon h mu of n. Okay, so now that we've got that stationary phase integral out of the way, I'd like to talk about this quantity here. So the rest of the expression, the thing that we actually have to compute with quantum field theory. So I call this the wave shape. So I'll give it a symbol, alpha HH of A. Psi S dagger, AHH, okay. Psi S. Now, of course, I know that I'm going to evaluate k this thing here at k equals omega n, but from the perspective of this computation here, this object, this just depends on the k. So we don't really have to worry about the relation between k and omega n in as far as we're dealing with this this thing here, this wave shape. And this wave shape, I mean, it's basically, it's up to the polarization vectors, they're just the Fourier components of the gravitational waveform. So up to the polarization vectors. So now what I'd like to do is simplify this expression. I mean, we've got the state psi here. I want to be talking about some classical kind of thing. So just like the discussion yesterday, I want to take advantage of the classical simplifications to write a more explicit expression for this that we could go ahead and evaluate in terms of amplitudes. Now the argument will be very much like yesterday. So many steps will hopefully look a little bit familiar. I'll start by expanding the state psi. So this thing will be given as an integral over the phase space of the particles inside the wave packets. P1, P2. So the wave packets have wave packets localizing the momentum of the particle in these kind of classical style wave packets. So there's sort of Gaussian wave packets with the property that the spread in momentum space is small enough that the mass is well defined classically, the momenta are well defined classically, and also small enough so that their Fourier conjugates, the positions of the particles are well defined compared to the impact parameter. So there'll be phi star for P1 prime, P2 prime, phi P1, P2. Our wave state psi had this exponential factor, e to the I b dot p, which translates one particle with respect to the other. So we'll have an e to the I b dot P1 minus P1 prime. I'm setting h bar equals 1, so we don't have to worry about that thing. Times now the plane waves in the state, P1 prime, P2 prime, S stagger. Okay. Now, the same caveats about the notation as before. These are really in states, and you can see it here because of the S matrices here. The S matrix, if time evolves us from P1, P2 in the far past, when the S matrix time evolves you to the future, then we have our detection, if you want, we have a measurement, and then we evolve back. S dagger is the time evolution operator that brings you back to the past, times P1 prime, P2 prime. So this is an expectation value on two states in the past. But if you look at this thing here, they kind of look like initial and final states, and I'm just writing the notation that way, essentially because of muscle memory. Okay, so we proceed again as yesterday by writing S as 1 plus IT. And let me just look at this matrix element here, so the bracket thing. So then we'll have P1 prime, P2 prime. S dagger is 1 minus IT dagger. You have the annihilation operator of 1 plus IT. Okay, so this is this bracket here. Now, if the annihilation operator gets to act directly on P1, P2, I'm going to get 0 for the reasons I mentioned earlier. Right? There's no gravitons in P1, P2. So that term, the unity there, isn't going to contribute because with this unity, the annihilation operator is acting directly on the ket. So I can forget about that term. In other words, replace the S matrix here with IT. But this S matrix is always going to be 1 minus IT dagger. So just like in the impulses, two terms here, always these two terms. So one term has an annihilation operator. The second term has P1 prime, P2 prime, T dagger, annihilation operator. So this really is very much like the situation for the impulse. At lowest order, we only need to worry about the first term, because when you expand out these T's, T's have, I'm thinking about working in perturbation theory. Actually, nothing I've done up to now has really relied on perturbation. It's only now that I'm starting to think about perturbation. But in perturbation theory, these T matrices have various coupling constant factors in them. So more T matrices is going to have more coupling constants, basically. Therefore, at lowest order, you only need the first term. And I'm just going to discuss the lowest order wave. But then there would be, there's only two terms, right? So in the annihilation operator acts on that one, I get 0. The annihilation operator has to act on this term, so it's always a T. And then there's a term with the 1 and a term with the T dagger. So there's always just two. Yep. This term. So now the annihilation operator is acting in its adjoint. So when it acts in its adjoint, it creates particles. Yeah, so the annihilation operator annihilates kets, but when it acts on bras, you get it. Okay. The lowest order, only the first term here contributes. Okay, so this first term looks like, maybe I'll just move over here. Yeah, well, the first term here is this annihilation operator, an IT. And the point I want to make here is indeed when the annihilation operator acts on this state, it creates a graviton, which kind of looks like an outgoing graviton. So this whole thing here, now at lowest order, maybe I should say that this is the lowest order T. So this expression here is now a matrix element of the transition operator from 2 particles to 3 particles. So this thing is an I, an A5 at 3 level, corresponding to the process P1, P2 goes to P1 prime, P2 prime, graviton with helicity H times the momentum conserving delta function. So the lowest order waveform is given by a 5.3 level amplitude. Good question. So remember, we defined creation and annihilation operators. Well, I defined them for particles, for heavy particles, but so they have the property, and let me leave out, well, let me leave out the helicity index for now. Well, this is how a creation operator acts. But then if I take the Hermitian conjugate of this, so that's how we define, in a sense, the annihilation operator. It's just defined by the Hermitian conjugate. Yes. Yes. Well, yeah. I mean, yeah. I mean, so this is acting in its adjoint. So you want to think about it like this, yeah. I mean, what I'm doing is I'm just using that AHHK. Yeah. Well, I mean, yeah. So this is a Fock space. So yeah. Yeah, so what this thing is defined to be is the action of annihilation operators for the particles times annihilation operators for my for the graviton. So that's this guy here, and these guys give you the P1 prime, P2 prime. So there's always a vacuum running around in the problem. It's always there. That's always the thing that you add your particles on top of the vacuum. So yeah, so each of these guys just acts on the vacuum. And you could think of this as, yeah, maybe those are enough words. Yeah, those were the words I was going to add, but didn't. Yeah, exactly. Yeah. So you could always think of it as being a tensor product of various, state spaces for the different types of particles you have. So there's some state space for the particles, some state space for the gravitons. The zero symbol is just the zeros for all of these spaces. And then these operators act in their different spaces. This sort of formalism with creation and annihilation operators is very handy because the symbol's always got to, the symbol's very reliable. So all you really have to worry about is the commutation relations or anti-commutation relations. We don't have fermions, so just commutation relations of particles and the various kinds of particles. Okay, good. Yeah, are there any other questions? Okay. Very good. So yeah. So in other words, this is sort of an intuitive picture here. This 5-point amplitude that's relevant here involves. I should make this a little bit bigger. Involves our particles coming in with momenta P1 and P2. Some particles coming out with some momenta. I'm going to change the value of the momenta, or I'll redefine them in a moment, but with momentum P1 prime and P2 prime, and the gravitational waves coming out. So, it's a sort of makes sense, right? This is why, this waveform, it makes intuitive sense that the waveform is made out of 5-point quantities. It is maybe worth saying that this cut term here, there's always this kind of a cut term, its job, or it can also be understood in terms of 5-point amplitudes. So when you start looking at the next leading order waveform, there will be a one loop 5-point amplitude from here. And this object will involve objects that are various kinds of cuts of one loop 5-point amplitudes. So you can always write this waveform in terms of one loop amplitudes, next to leading order, and 2, 3 loops, et cetera, at higher and higher orders. There is, particularly with this waveform, the structure here, this S dagger AS structure is very interesting. And although it is true that everything is, 5-point object, because there's this extra S dagger here, again, it's maybe useful really to think of this as being an in quantity rather than an in-out quantity. But it all depends on your perspective. So that's those comments just related to boundary conditions implemented in the quantum field. Okay, now I still haven't simplified the waveform by getting rid of these wave packets. So that's what I would like to do next. But yeah, I'm just going to focus on the leading order waveform. So I'll just extract this first term here, shove it in here, and then tidy up the wave packet. Restrict to the LO waveform. So the wave shape, the alpha at leading order, this thing here, I'll put an LO symbol on it to remind me that it's just the leading order value. Okay, so we have integrals over these momenta, the wave packets. And now I can insert, instead of this matrix element here, this expression. I'll just write it as IA5, comma 0, because it's the tree-level waveform times this delta 4. Okay, so to make progress, I'm going to change the variables of integrations in these p prime integrals. And I will do it sort of with reference to this picture here. So I'm going to redefine p prime to be p minus q1, p1 minus q1, and the p prime 2 to be p prime 2 minus q2. So the idea here is in the scattering, I'm losing some amount of momentum q1 from particle q1 and some amount of momentum q2 from particle q2. And I'm sorry, minus q2. Thank you. Thank you. Yep. So I'm losing a momentum q1 from the first particle, and momentum q2 from the second particle, and shooting that all out is gravitational waves with momentum k, which is q1 plus q2. Okay, so these integrals then, so there will be integrals d phi p1 prime, p2 prime, they'll become integrals with respect to q1 and q2. I have to be careful about the on-shell conditions for particles p1 and p2. So, so the integrals will be, well, I still have the integrals for the phase space integrals for particles p1 and p2. But I'm going to have integrals for momentum q1 and q2 too. Very good. Now there's the on-shell conditions for these particles. So now the on-shell conditions just say that p1 minus q1 squared should be on-shell. So I can write that as 2p1.q1 minus q1 squared, because p1 squared is equal to m squared because of this delta. You know, there's a delta function in here that's telling you that. There's a similar delta function for p2. And there are the theta functions, which say that p1 q0 q10 is positive. That is positive. And there are the wave packets. P1 minus q1, p2 minus q2, y p1, p2. In the exponent here now, there's going to be an e to the plus I, b dot q1, or 5.3 amplitude. And then this delta function is still there. it just sets Q1 plus Q2 equal to K. All right, and here's where I can feed in my classical simplifications. So in the domain, in the classical application of this method, the momenta, these Q1s are small compared to P1. Remember that we had this yesterday, explained that, that the Qs were smaller than the masses. So this would be true for Q1 and Q2. Yesterday, I just had one Q. So here, it's the case that both of these Qs are small compared to the masses. So in particular, these theta functions are always 1, right? So you're taking a small amount of momentum out of a big amount of momentum, so the theta functions are just 1. We can forget about them. These delta functions, I can also simplify them unless there's some singularities in h bar. Now, if you do the counting like I did yesterday for the h bars in these 5.3 amplitudes, you'll see that there are no singularities. Everything's very nice. But at 1 loop and 2 loops, etc., you have to be more careful. Then there are singularities. You need to cancel the singularities before you simplify the delta functions in this form. So without those caveats, that we need to be careful with the delta functions, we can simplify those 2 terms as well. They'll just become delta 2 P1.Q1 and a delta 2 P2.Q2. And in these wave packets, the Q1 shift is a small shift in what's on the scale of the Q1, a broad wave packet. So we can forget about this shift here and just write this as the norm squared of the wave packet. So our alpha will become integral d phi P1 P2 norm of phi P1 and P2 squared times integral d4 Q1 d4 Q2 delta 2 P1 dot Q1 delta 2 P2 dot Q2 thetas are gone. E to the I B dot Q1 times the 5.3 amplitude and the delta function, which just involves the momenta loss of the 2 particles being radiated into gravitational waves. Okay, now the integral over the wave packets at this stage, its job in life is just to concentrate the momenta p, in the rest of the problem at their classical values. So rather than introducing a new notation for that, we'll write it as these double angle brackets. Okay, and now we've reduced it to a nice form, right? So that is a form that admits fairly simple calculation in terms of amplitude. So what you need to do to actually get the dynamical information is always all in the amplitudes. So one needs to go ahead and compute what that actual amplitude is. I'm not going to do that here. What I've asked you to do in the tutorial is to go through this argument again, except for the electromagnetic case. Now it's pretty much the same thing. But you'll find that there is a very similar formula for the electromagnetic waveform just the radiation field generated by scattering charged particles. And then it's a straightforward computation, more or less, to figure out what the 5.3 amplitude is. So I've asked you to go ahead and do that. And you can just do it with Feynman diagrams. I mean, there are other more sophisticated ways of doing it with cutting, etc. But with this computation, at least, you can break it up in such a way that it's pretty straightforward to do it by Feynman diagram. So that's your exercise to compute this thing. Now, it's interesting that to think about soft physics in this context. And I thought that would be an interesting connection, given the lectures last week. So rather than going into a long discussion of soft, it doesn't have to be very long. What I've asked you to do was to compute this 5.3 amplitude in electrodynamics and then work in the limit where the outgoing photons have long wavelength. That's the soft limit. You'll find that the amplitude simplifies. And then you can recast this expression in terms of the impulse. So the conclusion is that the waveform, it's true in gravity just as much as in electrodynamics, the waveform in its soft limit is directly given by the impulse. And that's a reflection of memory. There is a memory in the gravitational waves because the particles have been deflected. Okay, now, so just some remarks about this. So just to finish. So if you compute the 5.3 gravitational waveform, the 5.3 gravitational amplitude, or the leading order version here, you reproduce a computation of Kovács and Thorne. So the 1 p.m. waveform, first post-Minkowskian waveform. So so that was first computed in the 1970s, late 1970s, 77 and 78. But the 2 p.m. waveform, the NLO, so the NLO version of this, so was computed for the first time just a few years ago. So computed with this method. So I say it's 2 years ago, but I think it's 3 by now. Yeah, 2023. Now, the first computation was performed, so that's one loop computation, but there are also these integrals here. So there's an integral of this type. I mean, I could do the Q2 integral, for example, with a delta function. Then there's an integral over the Q1 that's remaining. That's a Fourier transform integral. So that Fourier integral is non-trivial. It's actually the Fourier integrals which were quite hard. But more recently, last year, those integrals were performed analytically. So the paper I thought I'd refer you to is by Giacomo Brunello, Stefano De Angelis, and David Cassar. So I guess that's got sort of the most up-to-date version of this 1 p.m. waveform. I didn't write the archive number. The computation, though, so this next to leading order computation, so it was, the 2 p.m. was just done this way, so there's no alternative 2 p.m. waveform to compare with. But if you take it and you post-Newtonian expand it, there's, you can compare to, well, it's NPM, NPM, PN computations where they overlap. So where the post-Newtonian computations have been performed, you can compare. They were compared and they agree. There's some story about that, which is part of the motivation for what I'm going to tell you about tomorrow. Okay, that's all I wanted to say today.